There's an 810 kilogram dragster car and it's being decelerated by a parachute at 2.5 meters per second squared, as shown in this diagram below. And we want to find the tension in this cord. Okay, so we can definitely start off by drawing a free body diagram. So there's my force of gravity, there's my force normal, and we also have a tension in the rope here, which I'll label T. Now, when we create our F net equation for this particular problem, we're only interested in the forces from the free body diagram that are acting in the horizontal direction. So the force in the rope, the tension in the rope, is the only force that we consider for our F net equation here. Now, using Newton's second law of motion here, F net equals to m times a, and this is equal to the tension in the rope. Okay, so the mass of this particular problem is 810 kilograms, and the acceleration is 2.5, right? So the mass is going to be 810. The acceleration is going to be 2.5, and that's going to equal to the tension in the rope. And once we calculate this, going to a calculator here, the tension is roughly 2,025 newtons. So a fairly simple problem for this question here. Just make sure you draw the right free body diagram and create your F net equation there. Okay, let's take a look at another problem with a few more strings now. Okay, so in this next problem, we have a system of 3 blocks on a frictionless surface, and the system is accelerating at 2.0 meters per second squared. And we want to find the tension in the cord at X. Okay, so if we just consider the horizontal forces, and if we just draw the free body diagram by ignoring the force of gravity and the force normal, our free body diagram will look like this. So there's a force applied, which is pulling this whole system to the right. And this 4 kilogram block also has a tension in the rope like that. And I'm just going to ignore the force of gravity and the force normal there. And for the 1 kilogram block, there's also a force tension here. All right, and the red tension and the blue tension are equal in magnitude, and there's also another tension over here in purple. And for the 3 kilogram box there, there is a force tension like this. All right, and so what I'm just trying to say is this tension here in the black font and this tension in the purple font are equal in magnitude as well. Okay, so if I consider the free body diagram, all the forces in the horizontal direction, let's go ahead and create a F net equation for this entire system. So F net equals to, now this is going in the right direction, right? So it's accelerating to the right hand side. So we have our force applied in purple, and then we're going to subtract the blue tension. So that is all the forces acting on the 4 kilogram blocks. So I'll put that in bracket, plus now we got to look at the block in the middle, and the block in the middle is also moving to the right, correct? So we have the force tension, which is in the red font, and then we're going to subtract the purple font. Okay, so and then we're going to add another brackets here because the 3 kilogram box also has a force tension, and it's in the black font. Okay, so what I'm going to do for this particular problem here is let me just kind of put a subscript 1 here and a subscript 1 there because those tensions are the same. And I'll also put a subscript 2 here and a 2 there because those tensions are the same. Now, if I look at this entire problem here, it turns out that this tension and this tension, they just cancel out. So this tension, that tension just cancel out. And then if I look at this tension here, the negative T2 and this positive T2, those also cancel out. So when I look at my F net equation now, the only thing that really survives is the purple force applied. Okay, so we can actually calculate the purple force applied by solving this particular equation. And we're going to use Newton's second law here. So I need to look at the mass total times the acceleration, and that's going to equal to the force applied. Okay, so the mass total, if I go back to the original diagram, there's a 4 kilogram box, a 1 kilogram box, and a 3 kilogram box. So let's just add that all together. So 4 plus 1 plus 3. And then we're times that by the acceleration. And the acceleration for this problem is 2 meters per second squared. So times that by 2, and that's going to equal to your force applied. And then if we do the math here, 4 plus 1 is 5, 5 plus 3 is 8, and 8 times 2 is going to be 16. So 16 newtons is the force applied. Okay, so now that we know the force applied, we can go back to the original diagram here, and we can create another F net equation. And remember, our goal is to find the tension right here at X, right? So I'll label that T, and let's label this F applied. Okay, so what I'm going to do now is I'm just going to erase some of this here. I feel like I'm done with the F net for the entire system there. If I take a look at this 4 kilogram box here, let's go ahead and create, let's just go ahead and create a F net equation for the 4 kilogram box here. So F net would equal to the force applied minus the tension in the rope. And the purple force applied comes first because this whole system is moving to the right. So the force applied is going to be greater than the force in the rope. Okay, so F net, I can use Newton's second law here at mass times acceleration equals to F applied. Now we already calculated F applied, and that was going to be equal to 16 newtons, right? So I'll leave this as 16, and then we're going to subtract the tension in the rope. Now the mass for the 4 kilogram box is going to be 4, and the acceleration for this particular problem is still 2. And that's going to equal to 16 minus the tension in the rope. Alright, so now we have some simple math here. The tension can go on the left-hand side, and that's going to be 16 minus 4 times 2. And basically we have 16 minus 8, and 16 minus 8 will give us an answer of 8 newtons. So the tension in the rope is 8 newtons. So just going back to this diagram here, so basically this is going to be, I know I mentioned that this was the tension there, that's 8 newtons. And for the 1 kilogram box, when I had the red tension there, that's also 8 newtons, right? So both the tensions in the ropes are going to be the same because it's the same string there, okay? So that's something to know if you're solving some other problems in the future. Okay, great. Let's move on to another question here now. Okay, so for this next problem, we have a 0.055 kilogram bullet, and it's fired at 250 meters per second into a block of wood as shown in the diagram below. And then we're assuming an average force of 9,500 newtons to bring the bullet to rest in the wood. And we got to figure out what the distance, D, did the bullet penetrate the block. Okay, so a great thinking question here. And let's see if we can figure this one out here. So there's a few things we can do for this particular problem here. We know if it's being fired at 250 meters per second, that's kind of like your initial speed. And since the bullet stops right here, we can assume that your final speed is going to be 0, right? So if we take a kinematics approach, we know the initial speed is going to be 250 meters per second. The final speed is going to be 0 because the bullet does stop. And we want to find the distance traveled, right? So we're going to find the distance traveled. So we need one more piece of information before we can actually solve for the distance traveled by the bullet. And we can also use forces here to create another equation here to perhaps find the acceleration of the bullet. Okay, so we can say F net. Using Newton's second law here, we say mass times acceleration. And we know that the force here is 9,500, so 9,500 equals to the mass. Now the mass of the bullet is 0.055, so 0.055, and then we can solve for the acceleration there. Okay, so the acceleration is essentially going to be 9,500 divided by 0.055. And if we do the math on this, this will actually give us a very big number. So 1727.2727 meters per second squared. Okay, so that's the acceleration of the bullet there. And if I just kind of transfer that number over here, 172727.2727 meters per second squared, we can use that number now to find the distance traveled by the bullet there. Okay, so we have our initial speed, we have our final speed, and we have our acceleration. And now we need a kinematic equation that will help us find the distance there. And the kinematic equation that I have in mind here is this one right here, which is your final speed squared equals to your initial speed squared plus 2 times the acceleration times the distance there. Okay, let's go ahead and plug in the numbers here. Your final speed is going to be 0. Your initial speed is going to be 250 all squared plus 2 times the acceleration, which is 1727.2727, and then we go solve for the distance there. Okay, now when you solve for the distance here, you will get a negative answer, because if I bring this term to the left-hand side, we get negative bracket 250 all squared equals to 2 times all of this. And if we go ahead and solve for the distance there, it's going to be the negative 250 all squared, and then we divide that by just basically this number right here. So if I go ahead and transfer that down, I get bracket 2 and then times the 1727.2727. All right, so if we go ahead and calculate that, so we do actually get a negative answer. So we get negative 0.1809 meters. So mathematically, that's the number that we get. And I just want to say that this negative sign means that the bullet penetrated into the block in the opposite direction to its initial motion. So that kind of gives us like the sign there, but this right here gives us the magnitude right there, right? So that is what we are looking for, and this kind of gives us like the direction, right? So this is kind of giving us a displacement type of an answer here, but we're just interested in the magnitude there, and that's 0.1809 meters. And once again, that minus sign is there is because the bullet is penetrating into the block in the direction opposite to its initial motion there, so that's why there's a negative sign there. Another way that you can maybe think about this problem is by using a work equals to force times distance approach here. And we know the force here is going to be 9,500 newtons, and then we can solve for the distance there. But using constants related to work there, we know work is also equal to your kinetic energy. And that's going to be the 1/2 mass times your speed squared equals to all this. And this will also give you the right answer for D there. So I know this will be 1/2. The mass right here of this block is 0.055, and the speed that we have is 250 all squared. And you know, this answer also will give you the answer of 0.1809 meters, right? So you can also take a work approach to this particular problem. You just have to make the connection that kinetic energy is equal to the work done, right? So if you know that principle, then you can also solve for the distance using a work done method there. Okay, so that concludes this homework video guide.